A traditional warehouse runs on Excel that manually add and subtract number, copy paste data, and reconcile inventory by hand at the end of the day. One broken formula cells can corrupt the entire report and cause millions in losses. Agile Stop solve exactly this problem by boosting business logic down to database layer. And good morning, everyone. Today, our group will present Agile Stock, an enterprise inventory management system developed for our database management system project. Agile Stock was developed at a practical scale with around 1.8 megabyte of seed data, more than 30 API endpoints, and 9 database tables, and cloud deployment. The main highlight of Agile Stock is the database design. We implemented all 4 advanced database objects: view, ticker, store procedures, and user-defined function, and use them directly in the real system. For the tech stack, we use React and TypeScript for the front end, Fast API with Python for the backend, MySQL 8 on Avon Cloud for the database, and Docker Compose for logo development.
Next, let's look at our system's architecture. To keep Azure Stock fast and away online, we use a dual deployment strategy. When a user opens the app, our front end of ourselves sends secure requests to our backend on render. Then the backend talks to our MySQL database on Ivan Cloud over the secure connection. So now, let's focus on the most important part of our database, connection pool optimization. To handle the database connections efficiently, we configure the SQL Alchemy engine with 3 optimal parameters. First, PuSi equals 5. This keeps 5 connections open and ready at all time. It saves a lot of time because the system doesn't have to open the new connection for every request. Second, max overflow equals 10. This lets the systems open 10 exploratory connections during certain traffic spike. It prevents the app from slowing down under the heavy loads. And then more importantly, pull reaping equals true. This is our safety net. Every time the system grabs a connection, it runs a quick test query to check its health. If the connection is dead due to the cloud timeout, SQL Alchemy replaces it with a fresh one instantly. Thanks to this setup, Azure Stock completely avoid the famous MySQL has gone away error, making our system highly reliable in production. To finish our architecture setup, let's look at the backend model map. To make the code easy to maintain and help our team work together smoothly, we divide our business logic into 8 separate routers. First, in the government layer, feature auth handle secure login and create JWT tokens. Feature user manage employee accounts with strict role-play access. Second is the core operation layer. Feature catalog manage basic data for products and suppliers. Feature stock tracks all stock movements and trigger automatic database update. Finally, we have the advanced intelligence layer. Feature analytics power the real-time KPI dashboard. Feature AI forecasts run smart simulations to predict product demand. Moreover, the feature logistic process GPS coordinate for our live tracking map. Last but not least, the feature logs drive the real-time activity feeds using web sockets. This structure is exactly what allowed Azure Stock to scale efficiently. And now let's dive deep into our
group database design. First, we present the foundational relational schema of the Azure Stock system. Our architecture is built upon 9 core tables: roles, users, suppliers, warehouse, products, inventory history, shipments, stock adjustment, and activity logs. I want to draw your attention to 3 key design choices in the schema. First, the strict one-to-one relationship between product and inventory history. This table isn't just a passive ledger. It is the main data source that drives our automated database triggers. Second, the stock adjustment table. To guarantee a clear audit trail, it stores the old quantity, new quantity, and the exact reason for any manual changes. Finally, we avoid the standard float and use high-precision decimal for exactly latitude and longitude. This removes routing errors and it perfectly powers our live shipment tracking map. Now let's discuss about normalization. We built this database to prevent data anomalies, satisfying all forms to boycott normal form. For 1.5, every cell contains strictly atomic values. There are absolutely no nested arrays. For 2.5, we completely remove partial dependency by avoiding composite key. Every table uses a single in-auto increment primary key. For 3.5, we remove all transitive dependency. For example, row key is kept separate in the row table, so updating it only requires changing one place. Similarly, supplier name is stored inside the supplier table, preventing massive data duplication across products. Finally, boycott normal form. Because all non-key attributes rely only on our primary key, every determinant in the system is a candidate key. Finally, I want to highlight a true hurt of our ERD, our inventory history table. This acts as a central hub of our entire system. It is the main data source powering our automated trigger, bin cards, and AI forecasting. Specifically, please notice on the transaction type column, which only take in or out values. This is our main trigger point. The moment a transaction hits this column, it runs the automated stock update logic, ensuring a clean audit trail and absolutely consistency. Moving to our core database logic, we implement 5 advanced database objects to handle heavy lifting at the source. First, our trigger automatically synchronizes stock level the level a transaction is recorded. Second, store procedures manage complex adjustment, ensuring all inputs are validated before hitting the disk. For real-time insights, we use the app to calculate stock health metrics on the fly. Finally, we optimize performance using indexes for lightning fast lookups and view to aggregate warehouse data for our dashboard. This logic at the source architecture ensures maximum data integrity and system performances.
Now I will explain the inventory quantity update feature. As you can see on the screen is the SQL code for the trigger. Technically, the trigger is activated after data is added to the inventory history table, and it will identify the data at in or out to decide whether to add or subtract the quantity. This feature could be coded in Python, but we didn't use it because it would easily lead to recondition errors, causing the actual quantity to be inaccurate. And next, I want to present a problem that the warehouse system might encounter. The actual quantity doesn't make the quantity in the systems. Therefore, we set up a store procedure at the stock. However, another problem can occur when two employees update the inventory quantity simultaneously, leading to a conflict. Therefore, we do row level locking to ensure that when employee A is working on product X, the entire data line for X is locked. An employee B must wait until A finishes before continuing. And immediately after the new quantity is finalized, the procedure automatically runs an insert command to save the entire audit trail, including the old quantity, the new quantity, and the reason, ensuring absolute transparency. And after the input output data is securely recorded in the database, the next challenge is how to enable inventory management to quickly retrieve the history of any item. In practice, this is the inventory card, pin card hanging on the shelf. To digitize this card, our team designed the Get Bin Card API. The code displayed on the screen is the backend processing code using SQL Alchemy. We extracted the four most essential data columns: a date, transaction time, quantity, and unit cost. We also connected the user ID column to the user table to display the name of the person performing the transaction. The special feature here is either isoter equal true command, which is a left joint command in SQL intended to retain own bin card data even if an employee leaves and the card is deleted from the system. And now I will show you the bin card in our website. It is in the inventory hub section, and assuming that this is product. Yeah, as you can see, there is the date of the transaction, the type transaction, quantity, and the user who are performing that.
Now we move to the fourth requirement of the advanced database objects in our project, the table view to collect 4 different figures here: active units, low stock, in transit, and the net value. Why did we combine all 4 figures into one single view? Normally, to load 4 numbers, the system had to ask the database at least 4 times. That wastes so much memory and makes the screen load slowly. By putting everything into one view, we only make one single request. How does this help? It makes the dashboard load instantly and keep our servers running smoothly. Here we can see that the last 1, 2, and 4 are just basic methods. They give the managers the big picture: how many items we have, the total cash value in the warehouse, and how many items are in transit. But we can see here that the most highlight part of this code is in the low stock. We wrote a dynamic map formula using the C function. Instead of typing numbers by hand, the database automatically looks at the scale of each product, where how many us never have to manually type in set limits of thousands of products ever again. It is 100% automatically, with zero manual errors. And here is the website of our projects, and we can see here in the inventory hub page, and when we click that into the inventory hub page, all of the 4 KPI costs like active units, low stock, in transit, net value, they have been already calculated in the view tables, and by using the view tables, it helps us reduce a lot of memories, and it helps us our website load more smoothly. So that's why we use a views table and to calculate all of these 4 figures.
Our Smart Stock Alert system operates on a strict 3-layer backend architecture. Layer 1 utilizes a custom database UDF to automatically evaluate and track product stock statuses. Layer 2 leverages a precompiled SQL view that applies a dynamic, self-scaling formula for reorder levels, completely eliminating rigid, hard-coded limits. Finally, in Layer 3, our backend API accelerator, simply fetching the top 10 most urgent items for procurement. By confining heavy computational logic to this database, we keep our API incredibly lightweight and guarantee an absolute single source of truth.
Finally, here is the final requirement of the advanced database object in our project is the index. But here we use the implicit index. It means that my SQL automatically creates a B-tree index whenever a column is declared as primary key or unique without any additional SQL statements required. Why we use the implicit index? It has 2 reasons. First, it makes searching for data incredibly fast. It cuts down slow full table scan and changes them into fast OLAP and search. For example, when a user logs in, the system verifies their email almost instantly. Second, it completely optimizes our sort operations for complex parts of our system like logistics and analytics. The table connects seamlessly because the keys are already indexed. But the core benefit here is that we get maximum database speed and strict data security with zero manual and indexing overhead.
For segment tracking, we built an API endpoint called API Logistics Segment Map Data. The main goal here was to avoid the N+1 query problem. Instead of sending multiple separate queries for segment, product, suppliers, and warehouse, we combine everything into a single SQL query using a 4-table join. And this query retrieves segment information, product data, supplier location at the segment origin, and warehouse location at the destination. We also exclude deliver segment, so the map only display active segments that are all still pending, delayed, or in transit. On the front end, we React together with the leaflet.json to visualize segment route from origin to destination on an interactive map. Each segment status is displayed with a different color to easier tracking. And when user hover over a route, the tooltip shows additional details such as the vehicle type and the ETA, which is estimated arrival time. The backend is responsible for handling segment tracking logic and database communication when the frontend calls API Logistics Segment Map Data. Endpoint, the fast API backend executes a single optimized SQL query with 4 table joins to collect all required segment, supplier, product, and warehouse data at once. The backend then transforms the query result into structured JSON data, allowing the frontend to render segment route efficiently without sending multiple API requests. Right now, I will demonstrate the segment tracking feature on the website. On the homepage, we choose the segment tracker. Here, a search bar appear, and you can search by product name, the ID, supplier, or status. I will choose the status one like the in transit status. There are a lot of products that in this status appear, and I will choose the random one to see the map. Maybe the Corsa one. Here you can see on the map on the right of the screen, there is a product name, the supplier name, the origins, destination, quantity, and ETA appear. With this feature, you can easily track the real-time location of the product, monitor segment progress, and estimate delivery time. Next, I will talk about the print barcode function. This feature allows users to generate and print barcode directly from the dashboard. In our system, when users open the inventory hub, they can view detailed product information to see the barcode of a specific product. Users simply go to the item menu and select Print Barcode. The barcode image will then appear in the panel on the right side of the slide. Each barcode is generated based on the product ID using the code 128 barcode standard. When the user clicks Print Barcode button, the front-end sends a request to the Fast API backend API. The backend dynamically generates the barcode image and return it into the front end for review and printing. This removes the need for manual barcode creation and help warehouse manage product more quickly and accurately. The overall workflow here is user click the print barcode, the API generates the barcode image, and the system sends it directly to the print interface. In this slide, I will explain the backend API logic for barcode printing. We created an API endpoint called product ID barcode. When the front-end sends a product ID, the backend formats it into an 8-digit number and generates a code 128 barcode image. The image is then converted into base 64 format, so React can render it directly on the front end without storing image file manually. We also implemented API error handling to prevent system crash if barcode generation failed.
Now we move to our creative feature of our project, the AI demand forecast feature of our Astro Stock project. The goal of these features in our project is to shift from static inventory checking to proactive forecasting. Instead of using heavy machine learning models, we implemented a stochastic mathematical simulation. This approach guarantees a stateless architecture and zero latency performance for our project. The algorithm works in 3 stages. The first one is the extract historical baselines. We use a SQL query to group the outgoing transactions by day. Then we use the pandas library to calculate the average daily outflows. If a product is brand new or has no history, our code automatically calculates a safe fallback value of 5 units per day. Next, we project the future using a Monte Carlo simulation. Because reward sales fluctuates, our Python code applies a random variance between 80% and 125% to the daily baselines to visualize the uncertainty. We also calculate an expanding confidence interval, which rises by about 0.8% for every future day. Finally, we automate purchasing decisions. We use a SQL common table expression, or other name CTE, to calculate the consecutive 7-day consumption rates for all products. At the same time, if a product has 3 days or less of stock remaining, the system will mark its priority as urgent. It then recommends a restock quantity that covers the shortage plus of a 50% safety buffer. You can see here, this is the AI demand forecast page of our website. You can see here the actual stock project. Here is front end of the AI demand forecast page, and we have 2 more languages, English, Vietnamese, dark mode, live mode as well. Now turn back to the AI demand forecast feature. Here we have the forecast horizon that we can choose 3 options: 7 days, 14 days, and 30 days. So I will want to select 30 days, and here we can select the product and which one we want to predict. I will run this USB Type-C Thunderbolt 4, and now we want to run the AI model to see. Oh, here we can see that it has less us 3 numbers for us to know 6 days that before this product reaching 0, and we need to restock about more than 1,000, and it has been calculated based on the depletion rate, and here's the model confidence, 93.9%. And here we can see the depletion curve, and the blue line is the historical stock and the red line is the forecasted depletion. And the last one is the automated procurement recommendations, and this one has been coded by SQL CTE in the backend, and it had let us know the 5 most product need to procure. And here we can see that the predicted shortage, the recommended quantity, and the priority. That's all about the features and all about the diagrams and the numbers of our AI demand forecast feature.
Let's look at our WebSocket live feed. In a fast-paced warehouse, waiting for a page refresh is not an option. Here is our real-time flow. Whenever any action occurs, our Python backend logs us to the database and immediately fires a background broadcast. Our single-tone connection manager then takes this payload, loops through all active WebSocket connections, and pushes the session directly to the client. In less than 1 second, the React UI updates automatically. As you can see here on our web interface, we broadcast two main events, new activity log for seamless data sync and user status string for security, which instantly force a system-wide lockout across a whole device if an admin bans a user.
Moving on to the defensive core of our systems, database security and administration. Azure Stock implements a strict production-ready security model. Let's break down our authentication and encryption flow. At the storage layer, our database never stores password as a plain text. Instead, we use a bytecrypt library to hash them in automatic stocks. This makes a brute force attack impossible, keeping user identities safe even if the database leaked. At the gateway layer, when a user logs in, the backend immediately checks their account status. If the account is banned or inactive, the systems block them right away, even if they type the correct password. For verified active users, the backend creates the JSON web token using the HS256 algorithm and a secure key. This token holds the user ID and expires after 8 hours, balancing system securities and user convenience. Once authenticated, the system transitions into stage 2, the authorization flow. For every next request, the front end automatically adds the stored JWT token into the HTTP header. The backend uses the getCurrentUser function to capture this token. It checks the signature and expiration before any data action can start. Azure Stock Permission Systems is completely data-driven. Security flags like can view the analytics, can edit stock, and can manage users are pulled live from a roles table in the database. This means admins can change permission or add new roles instantly without changing any backend code. To handle high traffic smoothly, we bypass the SQL Academy ORM for checking roles. Instead, we run clean raw SQL statements. This choice removes ORM bugs entirely and prevents system timeout when multiple workers access the platform at the same time. The highlight is how we handle user lifecycle management through creative engineering. In a real business app, using the physical SQL delete to remove an employee's account is a bad design. It breaks database rules and causes crashes in history tables like inventory history. Azure Stock solves this with a soft delete via the deactivate endpoint. When an admin blocks a user, the system updates their status to inactivate. This locks the account but perfectly keeps the historical logs for future audit. To protect the systems while keeping JWT tokens lightweight, this deactivation works as a hard gate. The moment the database status changes to banned or inactivate, the security wall is locked. Any next login attempts or fresh API requests are blocked instantly with a 401 authorized response right at the gateway. At the same time, the system broadcasts a user status change event to update the admin dashboard in real time. This gives our security team instant visibility in live logs without making our lightweight JWT tokens heavy or complicated. It perfectly shows a smart and optimized security design.
Finally, I will summarize the main achievement of our project and several future improvements. During development, we successfully implemented all 4 advanced database objects: trigger, store procedures, view, and user-defined function. Directly in the production workflow, we also apply transaction management, role level, blocking, and rollback mechanisms to maintain data consistency and system reliability. Our database design follows 3NF and BCNF normalization with 9 relational tables, reducing redundancy while maintaining a complete audit trail. The entire system would also fully deploy on cloud platform using Virtual, Render, and Event MySQL. In addition, we integrated WebSocket and AI-related features going beyond the original course requirement. For future development, we plan to optimize performance feature by adding composite index and status index, implementing table partitioning for a large-scale activity log, and using read replica to separate analytic workload from transaction processing. This is all the future development you can see on the slide. Thank you everyone for listening to our presentation. We sincerely look forward to receiving comments and feedback from the lecturer so that we can continue improving and developing the further project.